Thank you for the invite. And I'm happy that you have summer because here in Michigan it's quite miserable weather. Okay, so here's the contents. Uh, so the talk is sort of backloaded. So I cannot jump directly to what I really want to say because certain things needs to be motivated and clarified in advance. And many thanks to Andreas Blas for going with me through the slides over and over again. Okay, so let me say a word as a lover of history. You know, when you look at ancient world, it seems that all starts with Greeks, with the Greeks. In fact, if you consider a period of time from the beginning of writing to the Greeks, and from the Greeks to our days, I think the first interval will be a little bigger. So there was quite a advanced civilization before the Greeks. So I know that when the Hebrews were uh, taken by the Babylonians to Babylon in 586 AD, then they were quite amazed to see these beautiful canals and the Tower of Babylon. It has 27 floors. And by the way, there was a common language of sorts, and it was cuneiform. So if Pharaoh of Egypt wanted to write something to King of Babylon, he used cuneiform. Anyway, but so there was the logic. The Greeks didn't start from the empty place, but the logic, as we know it, as a separate discipline, was certainly born in Greece and owes a lot of the democracy of the Greek city-states. So what has it to do with democracy? So in democracy, you uh, you need to convince your fellow citizens. So you need um, plausible arguments, and hence logic and the rhetoric and demagoguery, all that. And the height of Greek logic were Aristotelian syllogisms. Now, that was very insufficient for mathematics, but mathematicians didn't really need logic. Things were sort of under. You learn the necessary logic as you learn mathematics. That broke when infinitesimals were introduced. So here is a famous calculation uh, criticized by the bishop, I think Berkeley. So here is the computation of the derivative, and Berkeley said, "Wait a second. If this is equality, then dx equals 0, but then you shouldn't divide by 0." So obviously there was a problem. Leibniz defended infinitesimals as well-founded fictions like imaginary numbers. Newton didn't. He used infinitesimals, but not in his published work. When he needed to publish things, he would clean them up and use trigonometry and sort of classical methods of his time to get rid of them. So but infinitesimals allowed him to speak about evanescent quantities, which for him were kind of stages in a limiting process. So he was the one who actually invented the, the limits. So it took quite a while, but in 19th century, mathematicians, not logicians, notably Karl Weierstrass, developed this epsilon delta approach and eliminated infinitesimals from proofs completely. They remained because there was a tradition, so they remained kind of part of language, but in rigorous proof, they're not used. In the 1960s, Abraham Robinson uh, developed non-standard analysis. And uh, so provided a foundation to Leibniz's ontology. So, for example, that's computation that Berkeley criticized becomes very proper. So you put here you take the standard part, where the standard part of a number is so the numbers include not only reals, there are infinitesimals and infinitely big numbers, but every number in this extended set uh, can be uh, for each such number there exists at most one genuine real nearest to it, nearer than any other real. So that's what he called the standard part. And so you just take standard parts and it becomes completely formal and rigorous computation. So Georg Cantor actually didn't have this aim to found mathematics on sets. He was a mathematician. He worked with trigonometric series. He needed to compare sizes of sets of points. In this connection, he proved the uncountability of the reals and then proceeded to study transfinite numbers, ordinal arithmetic, and all that as a pure mathematics. Almost at the same time, Frege attempted to show that arithmetic is reducible to pure logic. And so in this connection, he introduced a form of modern symbolic logic. And then Russell, if I remember correctly, wrote to him a postcard with this. It starts very politely that I want to buy the next volume of your work. But by the way, there is this. Now, Zermelo, as Andreas pointed out to me, started to work on axiomatic set theory because before that he had a theorem that every set can be well ordered. And so he's proposed axioms aimed to justify his well-ordering theorem and prevent at least Russell's paradox. This eventually became the familiar ZFC. André Poincaré was quite at the end of his career, criticized Zermelo, pointing out in particular that it would be good to the beginning to prove that your axioms are consistent. And that hasn't been proved until these days. Nevertheless, ZFC, to all practical purposes, solved the crisis. So with these successes, logic became very popular. Andrei Kolmogorov and John von Neumann started as logicians. Alan Turing wrote his PhD in logic under Church. The universal machine suggested to von Neumann the idea of universal electronic computer, which made logic super popular. Now, I recounted this well-known story to derive a couple of lessons. One is the scope of logic kept increasing. It expanded dramatically during the crisis. Second, being slow, like what logicians were in dealing with infinitesimals, has a price. So non-standard analysis, which is a beautiful thing, it often simplifies reasonings, makes it much more intuitive, yet it has only niche successes and is largely ignored by mathematicians for, uh, I think, no good reason, but that's how it is. Okay, logicist AI. So in 1948, Norbert Wiener published Cybernetics, Control and Communication in the Animal and Machine. Arguably, it is the dawn of AI. The key idea, using his language, is that animals, machines, and organizations can be understood through common mathematical principles of information flow, feedback, regulation, stability, prediction. So in the second edition, he added two interesting chapters on learning and self-reproducing machines. So this edition was translated to Russian in 1968, and I remember when it appeared, and I was much impressed, but there was nobody for me to discuss these things, and I moved on with my own stuff. John McCarthy, Patrick Hayes, and others promoted symbolic reasoning as the essence of intelligence. So it was McCarthy who coined the term artificial intelligence in the proposal for the 1956 court conference in Dartmouth, which started AI as a field. So this approach was dominant from mid-1950s to mid or even late 1980s as a foundational vision of intelligence, shaping the field's philosophical aspirations and goals. In reality, of course, logic was too difficult to deal with, and so people definitely used procedural languages and heuristic paradigms and so on. But at least in principle, logicism ruled. So here is an interesting characterization from Michael Jordan from UC Berkeley. John McCarthy, by the way, this yellow color I use for quotations. And also I allow myself to edit quotes for brevity so that I can put them in on one slide. John McCarthy coined the term AI apparently to distinguish his research agenda from that of Norbert Wiener. Wiener has coined cybernetics to refer to his own vision of intelligent systems, a vision that was closely tied to operations research, statistics, pattern recognition, information theory, control theory, in fact, also to machine learning. McCarthy emphasized his ties to logic. In an interesting reversal, it is the Wiener's intellectual agenda that has come to dominate in the current era, under the banner of McCarthy's terminology. By the way, I don't mind questions in the middle. If you have something, don't hesitate to speak out. No, there's no necessity to wait till the very end. Here is from a book by Yann LeCun, one of the giants of current artificial intelligence. The book is in French. Interestingly, it kind of not so often happens. It has a Russian translation, but not English translation for some reason. How machines comprehend it, understand. While the heralds of the classical AI, based on logic, were pushing back its limits, the pioneers of learning started to make their voices heard. If we want to make computer system capable, like animals and humans, of complex tasks, logic is not enough. We must get closer to the functioning of the brain and make the system capable of self-programming. This research based on deep learning and neural networks is at work in all of today's spectacular applications. McCarthy was quite blunt about his ambition for logicist AI. I knew him very well, by the way. He stayed in our house, visited us, and, but I didn't share his enthusiasm for common sense logics and so on. Every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that the machine can be made to simulate it. So this, in principle, is a saving grace of sorts, because the expectation that logic alone could scale to general intelligence did not survive the test of reality. Surely logic contributes to AI and should contribute more, but it cannot be a sole foundation for AI. That is pretty much proved by the history of AI. So why this expectation failed? Basically because logicist AI mistook a powerful form of intelligence for the whole of intelligence. So let me explicate this. In the 1960s, Jerusalem psychologists Amos Tversky and Daniel Kahneman discovered that human thinking is driven by two distinct systems, System 1 and System 2. That's how let's say creatively they call their system, System 1 and System 2. So System 1 enables what they call fast thinking. It operates automatically and quickly with little or no effort and no sense of voluntary control. It supports innate skills that we share with other animals. It is good at detecting patterns and reading situations on the fly. It allows us to make snap judgments and decisions without deliberations, but it's prone to biases and errors. So let me give an example. When you study, say, how to bike, okay, you fall, you try to think about it, or you study driving. You know, your mother is sitting near you, okay, not with me, but with current often in this country this way, and tells you have to think about it. How do you forget? But eventually people learn, and you drive a car or you bike without even thinking on what you are doing. So everything is delegated to System 1. And if you think about it, a bike, in order to keep the bike stable, you have to solve extremely difficult mathematical problems. And they are solved, but you're not even aware of it. It just seems so easy and natural. And System 2 enables slow thinking, deliberate and conscious. It supports mental activities for example, complex computations. Uh, so Kahneman, who actually received the Nobel Prize for this research in formally in economics, because it was very relevant in economics, but essentially because there is no Nobel Prize for psychology. So he gives this example. So you can, you know, bike and think whatever you want. It doesn't stop you. You in the mean, at the same time, you can think about something else. But if somebody asks you to multiply to, 121 for 771, you probably will stop and think about it. So slow thinking is very different. Its operations are associated with subjective experience of agency, choice, concentration. It can override impulses and biases of system one, but it's much slower and requires more effort. So there is a beautiful book by Kahneman called Thinking Fast and Slow. Very much recommend if you didn't read it, just beautiful book. By the way, in those 1960s, every Wednesday I was in Jerusalem attending logic seminars. And during the lunches, several times people talked about Tversky and Kahneman, somehow more about Tversky. Tversky died relatively young, and that's why the Nobel Prize was given to Kahneman rather than to both of them. And it was on my agenda to visit, just was, so everybody seems to like it and praise it, but I never managed to come, which I regret. This Moravec's paradox from 1980s. Let's see, there should be somewhere. Right, 1988. So let me read it. In the early 1970s, some of the creators of successful reasoning programs suspected that the poor performance of robotics reflected the intellectual abilities of robotics researchers. I skipped something here. He says that such snobbery is not unknown in sciences. For example, it is a relatively common phenomenon how theoretical physicists look at experimentalists. His words, not mine. Eventually, it has become clear that it is comparatively easy to make computers exhibit adult-level performance in solving problems on intelligent tests, and difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility. Let me give an example. It's much easier to make computer to play chess on very high level. It's much harder to teach computer to play chess in real world, just to take a queen and move it without, messing up things. Since the first, that's what important. We come to the heart of his argument. Since the first multi-celled animals appeared about 1 billion years ago, survival in the fierce competition over such limited resources as space, food, or mates has often been awarded to the animal that could most quickly produce a correct action from inconclusive perceptions. Encoded in the large, highly involved sensory and motor portion of the human brain is 1 billion years of experience, about the nature of the world and how to survive. Reasoning is only effective only because it's supported by this much older and much more powerful, though usually unconscious sensomotorial knowledge. We all are so good in perceptual and motor areas that we make the difficult look easy. Abstract thought is perhaps less than 100,000 years old compared to the billion years that went to slow thinking, to creation of slow thinking. So lesson 3 from the spectacular fall of the logicist AI is we have to keep ambitions realistic. So it hugely underestimated fast thinking, the tacit knowledge that human intelligence depends on, and the power of machine learning. The question is no longer whether logic can model intelligence. It can't, all by itself. But what role should it play alongside learning? So we're going to address this question. Let me mention that this slow thinking has its own problems. It's often wrong. But let me give an example to see why even though it's often so wrong, it's so useful. So imagine you are somewhere in the prairies and you see something yellow. There's a slight chance that it may be a tiger. The probability that it's a tiger may be tiny, but you don't think about it. You just run away, which, from the point of view of survival, is a reasonable thing to do. But as instrument for estimating probabilities, we are extremely bad at that. That is quite well illustrated in the Kahneman's book. Okay, generative AI. So I'll speak mostly about LLMs because that's what I know a little better. So before we discuss logic, let's look at generative AI. What is it and how it works? How does it work? So at a high level, the task is this: given an input sequence of words. So technically, they deal not the words with so-called tokens, but let me ignore the difference. Select the next word according to the probability distribution in the given text corpora. So, and the text corpora for this large language models is huge, the whole internet. So it's about all that humans ever have written. So a priori seems, okay, you have probability distribution, sample according to this probability distribution. But do we know this probability distribution? Is it feasible? A priori, not at all, because maybe this particular sequence never actually happened anywhere in human history. So what is the probability of the next word? But we, the humans, we managed somehow. We learned how to speak and how to make sense. So apparently there are certain regularities in the language that can be exploited, not only these mythical kind of probability tables. So one breakthrough was that it was established that it's possible to convert words into real vectors, so that two vectors tend to be close if the words occur in a similar linguistic context. So the reason is that a word is characterized by the company it keeps. So if you take any English word, it has typically it has many meanings and occurs in many different contexts in a certain way. So if two words occur in a similar context, um, they can be coded by vectors in huge dimensional space, which the two vectors will be close. The problem with this is that the embedding is static, independent of context. And the more recent and crucial breakthrough that made large language models possible was the so-called transformer architecture. There was a famous paper from Google in 2017 called "Attention is All You Need." So the key innovation is the mechanism of self-attention. So I'll say a few words just to give an idea what is it. So given a prompt, this sequence of words, and a position, J, self-attention allows a model to assign weights, to learn some weights reflecting contextual relevance in the sequence. For example, consider this sequence of words. The animal didn't cross the street because it was too tired. And suppose now we speak about eat. So what does it refers to? So the self-attention allows, it's a technical notion, and it might give for it, for the weight, something like that. So to figure out the next token, self-attention prepares a context-sensitive, highly detailed vector for the last token in the sequence. So the last token, or the last word, in this case, tired. Let's see. Take a simpler example. Consider just initial segment. The animal didn't cross. Then this cross isn't just given all by itself, an isolation. The vector which corresponds to cross, now in this self-attention paradigm, since it attended to the, to animal, to didn't, so this cross reflects the meaning. I am a verb following an animal not doing something. Okay, this all encoded in this vector. By the way, there are two different approaches. So what I described now, it is how Google models work. So when you think about it, you can also look ahead. And, ChatGPT style models, they don't do it. They don't have look ahead, and instead of rely on sophisticated guessing. The description above is a simplified single pass view to help explain the basic idea. In reality, a transformer consists of a stack of quite a number of identical blocks. Each block has a self-attention layer with several heads working simultaneously. So one head is uh, busy with grammar, another with entity relationships, and so on. So illustration, admittedly imperfect and crude, but nevertheless gives an idea how it works. So imagine you have a paragraph, maybe in foreign language or in your language, but written, I don't know, by Hegel. And so you first pass, you identify the main nouns and verbs. Then maybe you resolve the pronouns and references. So this it, what it refers to, or this he refers to whom. Then the third pass, you understand causal logical relations. And fourth pass, you integrate across sequences. As a student, I tried to read Hegel, and uh, I really sympathize with this kind of sequence. By the way, in ChatGPT, GPT stands for Generative Pre-trained Transformer. So I'll speak about pre-trained in a moment, but it's important that it uses this transformer architecture. So animal learning and human baby learning is self-supervised. So baby appears there, it sits, and you cannot teach it anything. It needs to first. So the first it teaches itself, kind of self-supervised learning, they call it. And there is a goal in this self-supervised learning, and the goal is to survive in this world. So you better know where your mommy is, and so on. So large language models learn in a similar self-supervised way during the crucial and most expensive initial kind of learning, which for some reason called pre-training. I don't know why I need to ask ChatGPT or Gemini why it is pre-training, but it is the main thing. So when they speak about the training of LLMs cost hundreds of millions of dollars, or sometimes in billions. So this is the stage which is all this money, most of this money is spent. So after pre-training, LLMs undergoes additional stages of so-called fine-tuning, which is not self-supervised. It uses special data. So what is the problem? So the machine knows everything. So it knows how to say bad words, and it not necessarily uh, wants to speak very politely or understandably. And so you need to train it. Also, you don't want, it knows all kind of things like how to make a bomb at home and so on. And you don't want the machine to, to disclose this information. So that's the purpose of fine tuning, to put various guardrails. So a useful analogy is the pre-training is versus fine tuning is like baby self-learning versus schooling. So when a child goes to school, so they teach it, but you rely on something that the child understands you. And so and you can the teaching can change child, but only to a point. It's essentially a human being with certain things which will be there till very end. So LLMs exhibit something which looks very much as reasoning, convincing reasoning, but there are no normative guarantees that logic exists to provide. Uh, the other day, I asked uh, Gemini whether Tarski made such and such announcement, and Gemini came back said, yes, yes, yes. Here, exact reference. Okay, bulletin of 1948, 1949. Okay, I went to this bulletin, to the page provided. No, there was a couple of abstracts by Tarski, but not that one. And I tell Gemini, it's not there. Oh, I conflated. Gives me another reference. Doesn't work out again. So, and it's clear why. They do the reason statistical and plausible. So much earlier, I remember I asked, I think it was ChatGPT, to find a book. So it produced a bibliographic reference, some number of authors, I think two or three authors, and indeed those three authors had common works and could written this book, but they didn't. So it was a book with existing title, very plausible authors, but not the right one. Uh, so this problem is being solved, but it's a very difficult problem. And there are more pressing problems like safety and so on. Uh, so in general, the output is probabilistic, but plausible, not logically guaranteed. Co Coherence is statistical, not deductive. So reasoning is a kind of emergent, like with children, and unconstrained by logic. Oh, sorry. So during this crucial stage of learning called pre-training, there is no explicit representation of logic, whether syntax or semantics. It is not there in the architecture. Logic must be learned implicitly, and this is a problem. Logic imposes certain constraints. The model builds internal representation that correlate with semantical categories, with relations, with abstract concepts, but not to strict logic constraints. So this is why these large language models can, I'll just call them AI. This one AI can explain calculus, summarize philosophy, write code, mimic reasoning, yet also hallucinate and contradict themselves. Yes, sorry. LLM's intelligence. So LLMs turn words into features. So he speaks about features. Technically, it's kind of components of this vector of whose dimension is in millions. Um, and make these features interact, says Jeffrey Hinton, a great hero of machine learning. From those interactions, they predict the features of the next word. These millions of features and billions of interactions between features are understanding. This is the best model we have of how we understand. So it is not like there is a weird way of understanding that these AI systems are doing. And then there is how the brain does it. The best model that we have of how the brain does it is by assigning features to words and having features and interactions. And yes, he already admits that AI hallucinates, but so do we. Sorry. So let me say a few words about Jeffrey Hinton. Uh, Hinton, along with his student Yann LeCun, which I mentioned earlier, and with Joshua Benjo, a Canadian computer scientist, received the 2018 Turing Award for their works on deep learning. And they're commonly referred to as the three godfathers of the deep learning. Recently, John Hopfield and Jeffrey Hinton were awarded Nobel Prize in physics for foundational discoveries and inventions that enable machine learning with artificial neural networks. So it's not unreasonable, but notice that physics just expanded the notion what physics is. Let's see. Sorry, I jumped too quickly. So many, maybe majority, many people disagree with Hinton. The most common argument is that AI has the lights on, but nobody's home. They don't understand anything. So Stephen Harnert, a Swedish, I think, a philosopher, wrote already in 1990, a purely symbolic model is ungrounded. Its symbols are semantically interpretable by us, but they do not have intrinsic meaning for the system itself. Yann LeCun also somewhat disagrees with Hinton, but on a different level. He says that they are not truly intelligent because they're missing certain essential components: understanding the physical world, persistent memory, reasoning, notice this, reasoning and planning. By the way, this reasoning is everything here. Of course, you need reasoning to do planning. Understanding physical world is more kind of fast thinking in the sense of Tversky, Kahneman. Now, persistent memory, it's a very interesting thing. You sleep over it, and and then in the morning you suddenly understand something. How come? What happened? Well, there was some work done in the persistent memory, some kind of reasoning. Personally, I tend to agree with Hinton, though I would use the word intelligence instead of understanding, because understanding is somewhat subjective. Okay? I tell you, you seem to understand, but how do I know? Do you understand or not? Understanding is a kind of a subjective thing. Um, I may be wrong, but it seems to me that intelligence has many dimensions, but still can be somewhat measured, whereas understanding is something elusive. As Lacan implies, LLMs don't have human level intelligence, but intelligence comes in various forms and degrees, and will, artificial intelligence will surely be different from ours. So we have a good example. Aeroplanes don't flap their wings as birds do. So here's one interesting example of intelligence versus understanding is octopus. So it's one of the most intelligent animals, highly flexible behavior, fast learning in its own domain, exploration, problem solving, some tool use. But does it understand? Could be sort of down, hard to believe. Its nervous system is decentralized. There are these eight legs which essentially think. Uh, so it seems that its skills are primarily sensomotorial than conceptual. Okay, superintelligence. Zhvanetsky is a famous Russian, how to say, essentially a philosopher, but known as a humorist. An optimist believes we live in the best of all worlds. A pessimist is afraid that we do. So some experts, notably Eliezer Yudkowsky, which is a kind of champion of this direction, it started uh, at least 20 years ago, warn us about the existential threat of superintelligence. The danger, of course, the robots can become kind of evil, but not necessary. It may be a hyper competent machine doing exactly what it was told, like in the Odyssey, in the famous film. But let's consider the best possible scenario. Superintelligence not only does what it's told to do, but has highest regard for biological life, wants nothing else just to please us. Will make it us happy. It surely will produce. Notice we always use technology. We use our intelligence to produce technology. Now things are reversed. There's a technology producing intelligence. So it's a very different world. Now, surely we'll have uh, what Karl Marx called communism. Will produce a lot of products because we have much more intelligent beings, and all we do is the result of all we achieve is the result of intelligence. If we have higher intelligence, we'll achieve more. Yet it does not necessarily will make us happy. Recall the Industrial Revolution. It eliminated much hard physical world, but in the process, our muscles became weaker and bodies, by and large, thicker. What would happen to our minds with in the age of superintelligence or just advanced artificial intelligence? We probably will become feeble-minded and thick-headed. Maybe we'll have a kind of gyms for thinking. Like today we have gyms for exercising muscles. So there will be gyms for exercising our brains because in the real world somebody else will use uh, better brains. So logic is at crossroads. What will logic be in this age of AI? That's easy. I don't know. And as far as I can tell, nobody does. What can logic be? So this spectrum is huge. So, but let me look at the extremes. Uh, one extreme is that logic will wither away, will be absorbed into mathematics and other neighboring fields. Arguably, the process is well underway in math departments. So I tried to find some statistics, but didn't find any. I believe this view that logic may wither away is widely shared. But here is a concrete example. ETH Zurich, or ETH, Zurich once was a major center of logic. Paul Bernays and Ernst Zermelo worked there. So I first visited ETH in late 1980s. There were four good logicians there. Then, one after another, they retired, and none of the four was replaced by a logician. The other extreme is that logic will flourish and there will be logic departments in all major universities. Doesn't seem super probable either. But so there is a continuum of scenarios in between. Much depends on what we choose to play. Finally, what should logic be? What should it be? It's sort of presumptuous for me to say what logic should be. As Hebrew Bible says, katonti, too small, I'm too small for the task. But I want to focus attention on the issue discuss it. So I see three entangled objectives: direct contribution to AI, developing foundations, and expanding the scope of logic. As I expected, I have to be brief because the time is running out. So direct contributions to AI. So logic may, first of all, we shouldn't compete with learning. Learning does the heavy lifting. But there's a plenty of things logic in principle can do and should do. So we may contribute by making assumptions explicit, inference steps inspectable, and desirable constraints enforceable. Okay, let me call scaffolding. For example, today LLMs will um, easily deduce after pre-training without any fine tuning that being pregnant it statistically implies being female. But logic may impose a constraint and don't bother. More generally, logic impose quite known constraints that we do in our work for a long time, and certainly in computer science, type restrictions, arity. So when you speak about normal language, say in this context, this say verb has binary or ternary. Say give is a typically ternary. A gives B to C. You can write invariance, temporal ordering. The other way that logic can contribute by detecting contradictions, category errors, invalid generalizations, verifying consistency of arguments and plans, enforcing various domain rules, medical, legal. I'm not sure if there is a good word for all this, what can be called auditing. for lack of a better term. For example, it would be most helpful if it can dynamically to prove inconsistent partial hypothesis and reject candidate plans. This will make learning much more efficient. Finally, logic may contribute by formulating, tracking, and enforcing commitments. So the whole thing can be called governments. So the three roles for logic could be scaffolding, auditing, and governance. Foundations. To me, logic and foundations are very close. That's what attracted me to logic in the first place. Do we have a foundational crisis in AI? That is debatable. We certainly don't have a smoking gun like, Russell's paradox. But certainly there's a strain, foundational unease, so to speak. So we saw that reasoning is emergent and unconstrained by logic. This is one manifestation of this strain. Another manifestation is that the basic notions like intelligence, alignment, understanding are vague, certainly need clarification. One example Lacan mentions in his podcast he gave to Friedman. What is planning? So he gives an example. So he's sitting in a chair in his New York office. It was at the time when he was in NYU. Now he is a big boss at Meta. And he needs to get to Paris, to a particular place. So you need to plan. And plan involves great many levels of where you operate. You have to rise from your chair, walk to the door, and so on. You can arrive to, when coming to airport, you have to buy tickets. But eventually, to reach a particular place in Paris, I just want, the example is supposed to show how non-trivial planning is and how much it involves. And so these foundational problems will be solved, whether logicians participate or not. And if logicians are slow to an uptake, there's a price, if you remember, with non-standard analysis. Finally, scope extension. So as we saw, the scope of logic has been expanding. We should be realistic and keep our ambitions down to earth. Still, there's no reason for the scope expansion to stop right here, right now. So traditional logic has been the science of correct reasoning. But recall, the logic came from these convincing arguments. So there are many ways to expand logic in different directions, but one direction is to expand it to other forms of convincing argumentation. Certainly, Bayesian logic, Bayesian logic, and probabilistic reasoning in general, it's logic. It's called logic, but it's not done by logicians. It's mostly done by probability theorists. Now, rhetoric and demagoguery, you may not like them, but say demagoguery, but they have certain logic of their own. Maybe even thinking, the fast thinking in the sense of Kahneman can be incorporated. That's it.